All right, so today we're going to take a look at our next two conic sections, ellipses and hyperbolas. So we've already seen hyperbolas when it came to rational functions, but these are just a little bit different. And just like parabolas, they are rotated around in different ways than we've seen before. Ellipses are just a fancy word for ovals. So here are the equations of ellipses that are centered at the origin. So nothing real special about them. They are actually going to be very similar looking to hyperbolas when we see those in a minute. The main difference here is that, we'll talk about that later, but now you'll see the x squared and the y squared on the top. Whichever one is the direction of the orientation of the ellipse, so which one's the longest side, goes first. So horizontal means that the x is first, vertical, so it's longer in the up and down direction, the y goes first. The a squared on the bottom is the radius of that part, so the vertical radius, I guess, or the horizontal radius, depending on which one goes first. And regardless, it's the longer radius, and b is the shorter radius. So ellipses have two radii. So this first one, we were just given an image of the radius, and we want to, of the ellipse, and we want to go ahead and come up with the equation for it. So the basic form of this, again, this one is vertical because you can see that it is longer going up and down than it is going left and right. So it is switched up a little bit. The y squared is going to go first over a squared plus x squared over b squared. And these are always equal to 1. If you ever have something that's not equal to 1, you need to divide that number out so that way you end up with a 1 on the other side. Otherwise, you don't have your full equation for an ellipse. So our center is at the origin, which is where it needs to be. We haven't seen what the equation looks like without that yet. So now we just need to look at what our two radii are. So what A is and what B is. So again, A is the longer of the two radii. So that's going to be the vertical one going up and down. So it's up 1, 2, 3, 4, 5. We can see the point is given to us as well. It's at 5, 0, 5. So A is 5. And B is going the other way, left and right. So it's over 1, 2, 3. So B is 3. So now we just need to fill those in and then square them, and then we have our answer. So y squared over 5 squared plus x squared over 3 squared equal to 1. 5 squared is 25, so it's y squared over 25 plus x squared over 9 equal to 1. And that is the equation for this ellipse. Just an FYI, I'm going to go kind of quick on these videos because I want them to be short, but I want you to be able to go back and watch them over and over as many times as you need. So here's what they look like whenever it is not necessarily centered at the origin. I like to just use this in general. That way if it's centered at the origin, I cover my base, or if it's not, then I'm good that way too. H and K are the center, and that just means that our center would be 0, 0, and it'd be x minus 0, and y minus 0 does nothing to it. So it looks the exact same as it did before. It's the only difference. Big change here is that the foci and the vertices will change based on where A and B are, or where H and K are, sorry. You just add the A to it if it's shifted left or right. If it's horizontal up and down, you add that to the K instead. It kind of just depends on the orientation of it as well. So this first one here, we want to write the equation of an ellipse. We don't have an image of it. We know where the vertices are. We know where the co-vertices are. So that means we can figure out the midpoint between these 2 points for each of these. So the midpoint between the vertices, midpoint between the co-vertices, and that'll tell us where those things are, or where the center is. We really don't have to do it for both, but we can just to double check it if we want to. So we have to use our midpoint formula, which again is x1 plus x2 over 2, and y1 plus y2 over 2 as an ordered pair. So we're going to do that for, it doesn't really matter which one we use. So we can do negative 6 plus 4 over 2, and negative 2 plus negative 2 over 2. So that gets us a negative 2 over 2. and a negative 4 over 2, which simplifies to be negative 1, negative 2. Now, if we want to do it the other way, use the other 2 points, we can do that as well. It would be negative 1 plus negative 1, which is negative 2 over 2, which gets us the negative 1 again. And then negative 4 plus 0 gets negative 4 over 2, which is negative 2 as well. So this is our center. So now we have our HK. We're good to go with that. Now we just need to figure out the distances between our 2 points, or the distance from the center to the other points. So the advantage here is that we can see for the co-vertices, the x value is the same for both, right? They're both negative 1. For the y values, they're both negative 2. So that means we really only need to look at the opposite ones that aren't the same. So for the vertices, the negative 6 and 4. So really all we need to do, we don't really need to look at both of those points. We can look at the center, or we can look at those 2 points and just divide by 2. That's fine too. So that negative 6 and 4, what we would want to do is find the total amount between them, right? So negative 6 minus 4, or you would want to do 4 minus negative 6. So that's 10. And you divide that by 2. And both parts you want to divide by 2. So that's going to be 5. So that's going to be our A, more than likely. And the other one, we do the same thing. So 0 minus negative 4 divided by 2 gets us 4 over 2, or 2. So that's our B. So now we have our center, H and K. We have our A and B. We make our formula, or our equation. So the formula again, x minus h squared over A squared plus y minus k squared over B squared equal to 1. So just fill in the things we know and square where we can. So x minus our h is negative 1, so it's, instead of minus, this will be plus. And our a was 5, so 5 squared is 25. Y minus negative 2, so it's plus as well. And 2 squared is 4. So there is our equation. This next one, a listener is standing in an elliptical room, 150 feet wide, 320 feet long. So those are our 2A and 2B, the whole lengths of our axes, or our radii, or I guess diameters. When the speaker stands at one focus and whispers, the best place for the listener to stand is the other focus. We're going to write an equation to model this ellipse, assuming the major axis is horizontal and the center is at the origin. So we're back to center at the origin, which means our h and k are 0 each. So with that, we know, again, we're using x squared over a squared plus, now it doesn't say which way, it says the axis is horizontal, so x squared first. So we just need to figure out what a and b are, and that's just half of the two lengths, right? So 320 is the larger of our two numbers, so that's going to be our 2a. So we divide both sides by 2, and a would be 160. Now we have to square that for our equation, and that's a very large number. It is 25600, or 25,600. And then 2b is the 150, so dividing that by 2 on both sides, we get b equal to 75, and b squared is 5,625. So now we have our two numbers that go into our equation, and that's all we have to do. So x squared over 600 plus y squared over 5,625 equal to 1. pretty easy for all those words. Now, this one's a little bit more complicated because we have to actually manipulate our equation. And to do that, what we have to do is actually complete the square twice within the same equation. So we need to do some rearranging of our equation first. And there's not a ton of space to do this problem, unfortunately. So what I'm going to do is I'm going to write over the problem and give myself a blank slate. So it's x squared plus 4y squared minus 6x minus 16y minus 11 equal to 0. So now I'm going to give myself a whiteboard to use to find this, and then we'll go back to the problem itself. To graph it, that is. So there's our equation. What we need to do is put all the y's and x's together and move that 11 over to the other side. So we got x squared minus 6x plus 4y squared minus 16y equal to 11. So now we have everything lumped together. We are going to complete the square with both of them. So we're going to have an x squared minus 6x plus some number plus, we're going to factor out a 4. So we have y squared minus 4y plus another some number equal to 11. And since it's on the other side of the equal sign, we can go ahead and add it to both. So plus the number in the first parentheses plus 4 times the number in the second parentheses. We have to make sure we multiply by 4 because that's what we're doing for the second parentheses too. So now we need to figure out what these blanks are. So the first one, we're going to take that negative 6, divide it by 2, and square it. It's the process of completing the square. So we end up with negative 3 squared, or 9. So that's what we're going to put in the blank. And on both sides of the equal sign. Okay, do that same process with the negative 4 in our second parentheses. So negative 4 over 2 squared. It's going to be a negative 2 squared, or 4. So that goes into both of our second blanks. So now we have two perfect square trinomials with our two parentheses on the left side. So that means the first one is now going to be x minus, since the 6 in the middle is negative, and or actually it's just this number here, the negative 3. So minus 3 squared plus 4 times y minus 2, so the negative 2 squared. And that is equal to all this stuff on the other side. So we've got 11 plus 9, that's 20, plus 4 times 4 is 16, so 20 plus 16, 36. So now remember what I said earlier, we want to have a 1 on the right side. We don't have that, and we don't have our fractions on the left side. So what we need to do is divide everything by this 36. So that'll make a 1 on the right side, and it'll make some fractions we can simplify on the left. So the first one's good how it is. There's nothing really we can do about it. So that's going to be x minus 3 squared over 36. Plus 4 goes into 36 and even 9 times. So that means we have y minus 2 squared over 9 equal to 1. Not sure why my wrist keeps coming up for marks here. So now we have our equation. We know our a is going to be the square root of 36, which is 6. Our b is the square root of 9, which is 3. And we know our center is at 3, 2. So we pretty much have everything we need. Ellipses, you don't have to have a lot of stuff in order to graph them. So that's really all we need. So I'm going to go ahead and copy that. I'm going to erase everything on my screen. Get rid of this image. I'm going to put all that stuff we just had on here. Maybe a little bit smaller for the equation, but there we go. So again, we know our center's at 3, 2. So there's our center. Our A is 6. So that means we got to go out to the right 6. Out to the left 6. Our B is 2, so we go up 2. and down 2. And now we have to just make our ellipse. So I have a nice fancy tool on here that can make this for me. As close to the center as I can get it anyway. And there we go. There's our ellipse. Oh, you know what? I've noticed I just did that. I didn't do the vertical axis the right. It's 3, not 2. There we go. Now we're good. And there's our ellipse. So pretty complicated when it's not in standard form already for an ellipse, unfortunately. So now we're going to take a look at hyperbolas. So hyperbolas, the difference here is that it's a minus inside instead of a plus. That's really it. If, again, the x is first, then it's the horizontal orientation, which means that it looks like this. If it's vertical, it looks like this. So before, when we looked at ellipses, they were actually kind of diagonally orientated, and now they're going to be up and down orientated. So that's the difference between rational functions and conic sections with that, especially because they basically create it so it's not a function anymore. That's why conic sections are not functions. So here, not all of them anyway, some parabolas can be, right? So here we have an equation for the hyperbola shown. Again, just like we started out for the last one, this one is vertically orientated. So again, we need to do the y squared first. So it's y squared over a squared plus, not plus, sorry, it's minus now. It's a hyperbola. X squared over b squared equal to 1. Also equal to 1, just like ellipses, so you do have to be careful about that. So here, it's not as easy to find a and b. So a is easy. A is just the point between your two, like the two vertices of the two parabolas, basically. They're not really parabolas, but the two vertices of your hyperbola. So the 0, 2, and 0, negative 2 tell us that our a is 2. Now, C is a little bit easier to find. C is a special number, but if you look back at the last slide, it shows that C is where the foci are. So C is 4. Now, you're probably wondering, well, what's B then, right? We don't know. But we can find it using Pythagorean theorem. So, remember, a squared plus b squared equals c squared. That applies to these three as well. So B, it just goes out a little bit further, right? So what we need to do is figure out what b is. So plug in our numbers. So 2 squared plus b squared equal to 4 squared. 2 squared is 4 plus b squared equals 16. And then we just need to subtract 4 from both sides. The nice thing here is that we don't actually have to continue to solve for b. We really just need to know what b squared is. Because in our equation, or the formula, it's b squared, not b. So that's just 12. So now we know what a is. We want to know what a squared is. That's just 2 squared is 4. We already did that in the process of finding b squared. So now we have a squared, we have b squared. We can just go ahead and plug them in. So y squared over a squared is 4 minus x squared over b squared, which is 12, equal to 1. Now, the big difference here between ellipses as well, aside from it being subtraction, and the orientation part stays the same, right? Y squared is first because it's the one, the direction it's going, right? But a squared also stays going first, no matter if it's the larger number or not. So before, a squared was always the largest number, and that's why y was above it. Now y is above it because of the orientation of the figure. Really, that's the case in both, but a squared for ellipses is always going to be bigger, so it's always going to go first. So our next one here, the asymptotes for a vertical hyperbola are at y equal to 3x and y equal to negative 3x. And the vertices are at 0, 2, square root 10, and 0, negative 2, square root 10. We're going to write the equation of the hyperbola. So here, knowing what, oops, sorry about that. Going back, I accidentally clicked instead of starting to write. So these plus or minus 3x's that we have, that comes from an equation that was on that first slide about these, and that is equal to plus or minus a over b x. And we know that because it does tell us it's a vertical hyperbola. If it was a horizontal one, it'd be b over a instead of a over b. It's the only difference. So our plus or minus a over b is equal to 3. So now we have this 2 square root 10 part that the vertices are at. Again, we know that vertices are what a is. So a is equal to 2 square root 10. So that means we just plug that in here. 3 equal to 2 square root 10 over b. And we can get what b is. That's 2 square root 10 over 3. Now we need to square that in order to get our equation set up. So b squared is that whole thing squared, which would be 2 squared. So I'm going to have to work this out. There's a lot to it. So that's going to be 4. The square root 10 squared is just 10, and the 3 squared is 9. So that's going to be 40 over 9. So now we have a, we have b, we have those parts of our equation. So we're good there. We do need to square a. Which is 4 times 10, or 40. So now we have a squared, we have b squared. We know the direction it is in. And again, we have not looked at anything that's not centered at the origin just yet. So we are ready to go. This one's going to be x squared first, because it is... Oh, sorry. No, it's y squared first because it's vertical. I'll write that a little bit different. So that's it. Kind of funky looking with the 40 over 9 on the bottom, but that's what it is. So this next one, we're going to start looking at hyperbolas that are not centered at the origin again. Again, the only difference here is that we add in those parentheses on the numerators of our two fractions. So it's x minus h, y minus k. It's always in those groupings. Just, again, depends on if it's horizontal, which x would go first in, and vertical, y goes first in. It's the only change. So here we are given one. We want to graph it and identify the vertices, foci, and asymptotes. So let's do that before we graph it. So the vertices, those are easy. Well, one of them is easy. A is equal to the square root of 4 or 2. The center, now it doesn't say to find the center, but you want to know where that is so that you can kind of figure out where the graph is going from there. So the center is going to be at, this one's x first, so that means its direction is horizontal. So it's at 3, negative 5. And we want to find, just as the vertices, we got the vertices from A should be at, again, this one's going left and right, so that A being 2 is going to shift it 2 in both directions in the x. So that means it's going to be 1, negative 5, and 5, negative 5. And the asymptotes, so there's a formula for that. That was the y equal to plus or minus a over b, but now we're going to be looking at b over a because it's a horizontal x. So now we need to know what b is. We don't have that, but b is just equal to plus or minus 9, so that's or the square root of 9, or just the square root of 9. So it's 3. So it means our asymptotes are at y equal to plus or minus 3 halves x. So that kind of helps you when you're graphing it, because then you know kind of which line it's getting closer and closer to. So I'm going to still draw those on there too. So our center is at 3, -5. So that's not really part of the actual graph of the line, but it's part of the process of graphing it. That's the point where these two lines are going to cross, the asymptotes. So out 2 in both directions for our vertices. And then let's draw these two dotted lines that we're going to put on here, our asymptotes at plus or minus 3 halves. So we have the point, the center, that's where those two are going to cross. So our slope is just going to be 3 halves with that. So we're going to go up 3 to the right 2 a couple of times, and up 3 and to the left 2 a couple of times. And the same thing going down. Just so you have an idea as to what we're trying to avoid, basically. So those dotted lines are going to be where the curves get closer and closer to. So instead of having to find a bunch of points, our graph is going to look something like this. Just getting closer and closer to those dotted lines, but not crossing them. So number 8. This one's a bit confusing when you read it, but it's not too bad of a problem. The LORAN navigation system is based on hyperbolas. 2 stations send out signals at the same time. A ship notes the difference in the times at which it receives the signals. The ship is on a hyperbola with the stations at the foci. Suppose a ship determines that the difference in its distances from 2 stations is 50 nautical miles. We want to write an equation for the hyperbola on which the ship lies if the stations are at -50, 0, and 50, 0. So those are the foci of our equation. And again, our foci, since this is given to us in a graph, it's horizontal. The foci are at h plus c, k. So since our k is 0, h is 0 as well, right? Because you can see in the picture the center of the origin. So center hk 0, 0. So our c is 50. This is 0, 0 plus c. So c equals 50. It's really plus or minus c too. So now we know what our c is. Using that 50, we know that the difference in our a is going to be 50 divided by 2. The distance between the two the difference in the distance between the 2 stations is half of that, so 25. That's our a. So now we have a and c, we just need to find b, so we can make our equation. So again, remember using the Pythagorean theorem, I'm going to write it out with it solved for b already, actually b squared already, because that's what we really want. And that's going to be 50 squared minus 25 squared, which is going to be 2,500 minus 625, which is 1,875. And we also, in that process, got what a squared is, which is the 625. So now our equation, again, this one is horizontal, so we start with x squared It's centered at the origin, so we don't have to add anything to the x. And so that's going to be x squared over our a squared, which is 625, minus y squared over 1875 equal to 1. And that is it for these notes.